Welcome to the second lesson in the thermochemistry chapter. And so this time, you're going to be able to qualitatively predict the sign of a standard delta S for various processes and calculate the value also for various processes. You're going to understand the relationship between delta S in the universe and delta G of the system, which means you'll also know what G stands for. And you're going to relate these thermodynamic quantities to equilibrium constants and reaction quotients. It's not as bad as it seems. All right, but first, a quick review of what we've talked about before, namely the second law of thermodynamics. And so the second law of thermodynamics simply stated that the entropy of the universe was always increasing. And just to hit home how important that is, I'm going to do it in a couple languages for you. So in Spanish, la segunda ley de la termodinámica, la entropía del universo siempre está aumentando. In French, la deuxième loi de la thermodynamique, l'entropie de l'univers ne cesse de croître. Haitian Creole, deuxième loi thermodynamique, l'entropie de l'univers a toujours augmenté. And let's see, I can also do this in ASL, I think. So, second law, heat, motion, universe, whole, disorder, always increasing. So it's that important. And a quick review of the third law simply stated that the entropy of a perfect crystal at 0 Kelvin is 0 joules per Kelvin. All right, so what's on deck for this lesson? We're going to talk about, again, get deeper into the nature of spontaneity, talk about the entropy of the universe, and we're going to introduce a new thermodynamic quantity, namely Gibbs free energy, which will be our, in the end, true signpost of spontaneity, and then talk about its relationship to equilibrium. All right, so entropy and spontaneity. So we've talked about this a little bit. So if you have a sample of, let's say, gas phase sodium ions and of gas phase chlorine atoms, and have the misfortune of allowing them to come into contact with each other, there'll be a blinding white flash, and then there'll be a white powder covering everything around you, and that white powder would be solid sodium chloride. So this reaction is very spontaneous and also gives off quite a bit of energy. But on the other hand, at no matter what temperature, on the other hand, liquid water will spontaneously change to solid water only if the temperature is below 273.15 kelvins. So we need to develop some formalism. Now, and the other thing to note about this first reaction is it's spontaneous even though you've got two gases making up a solid. So this doesn't seem like it would be increasing the disorder of the system, because clearly it's not. And in this case also, when it happens spontaneously, liquid's going to solid. So here we've got two things that clearly seem to be an increase in order, but are spontaneous under some conditions. And the important thing to realize is that when you're talking about this being an increase in, this being a decrease in disorder, and this being a decrease in disorder, we are talking about the order or the disorder of the system. And the second law very clearly states that it is the entropy of the entire universe that is always increasing. So you can think of a couple of scenarios here. And so remember, the overall signpost here is that the entropy of the universe must always be a positive quantity. And so there are some cases where the process has an increase in the system entropy and also managed to increase the entropy of the rest of the universe. So both of those are going to add up, and then the delta S of the universe will most definitely be increased. So that's going to be spontaneous no matter what. Now, this is the case if this is exothermic. So let's keep that in mind. Now, if the process is endothermic, so what could you have here? You could have a process where, I'm sorry, yeah, this is still an exothermic process. Now, you could have a process like this where the increase in entropy of the system is negative. So this would be the sodium and chlorine making sodium chloride. But by giving off heat, it creates disorder in the surroundings. And as long as the disorder change in the surroundings is larger in magnitude than the disorder change in the system, the overall disorder change of the universe is a positive quantity. You've got spontaneity. Now, you might also have cases like our ammonium nitrate cold pack system, where the the system represents an increase in entropy. So in this case, you are dissolving a solid, but it's endothermic, so that it requires heat from the surroundings to happen, so it cools it down. So that means that there's a decrease in the entropy of the surroundings. But as long as the increase in entropy of the system is larger in magnitude than the decrease in entropy of the surroundings, the increase in the delta S of the universe is still a positive quantity, so that still works. So a increase in system order or a decrease in system entropy, like this case B right here, can still be made spontaneous, such that the increase in system order is offset by a greater increase in the disorder of the surroundings. So as long as both of these add up to something positive, it's going to work out. The fourth case, where both the change in entropy of the system and the change in entropy of the surroundings are negative, in that case you're adding two negative quantities, so that's going to make a negative delta S of the universe. So there is no way that particular process is ever going to be spontaneous, which is why it's not on this graph. Now, the problem with this is that the delta S of the surroundings can be tricky to determine. The system is usually the beaker of stuff that you're looking at. The surroundings is the rest of the universe, and that's a lot of stuff. So people spent a little bit of time and some mental effort to try to figure out a better way to express this entire equation to give you a delta S of the universe in a way that it's a little bit more easily calculable.